How do the navigators do their circles equal altitude? Drawing circle of equal altitude.
So I keep saying that if we're living on a globe, then the geometry should also work on a globe. And I think it's a misconception that people have, is that a circle of equal altitude on the globe will actually look like this.
Flatzoid may well chuckle, but there's an easy way to check the geometry, and that's to do it yourself. So let's start off with a sphere, centred at the origin, with an Earth-like circumference of 21,600 nautical miles. We can put a point on it representing the ground position of a star. The observer has already worked out the co-altitude angle for that star, and is currently some distance from its GP. Now I'm not going to multiply anything by 60 to get a radius, and I won't be going anywhere near GeoGebra's circle tool. I won't be using any equatorial planes, coordinate systems, haversines or right triangles. In fact, there won't be any hypotenuse in sight. Instead, I'm just going to rely on geometry and do something with an angle. Using the observer's co-altitude angle, we can slice through the sphere with the plane, and it's easy to see where they intersect. And our observer, let's call him point B, is somewhere on this path. Given the angle in the slider, can anyone guess the surface distance from the GP to the observer? Well, let's draw it in and find out.
Wow.
Now I don't know about you, but the only teardrops I can see here are the salty ones trickling down Flatzoid's cheeks. This is no misconception. Flatzoid can deny it all he wants, but in doing so, he's also denying geometry.
I don't understand how it's so difficult to understand. This demo he's doing is taking the measurements from a flat horizontal baseline, a plane, and just giving it a duplication to say it's on a sphere. This arc length, guys, is based on perspective. It's a celestial sphere arc length, which is just your field of view to the star. The actual apparent angle measurement is done from a horizontal baseline, which is literally proving right now because of 90-degree base.
Let Flatzoid speak, and he'll tell you himself that he hasn't got a clue by way of copious amounts of word salad. You only have to listen and then wonder how anyone with even half a brain cell can be taken in by him. Of course he couldn't debunk any aspect of Proto Thad's demonstration, so I thought I'd have a stab at verifying it.
It starts with a sextant site of Saturn at 24 degrees 7.0 arc minutes, followed by Shadar at 39 degrees 36.2 arc minutes, and finally Altair at 55 degrees 33.8 arc minutes.
Before we look at Proto Thad's measurements, let's take a moment to discuss these ones. So here I've expanded the script to draw 3 circles of equal altitude based on some angle measurements to stars which were taken at these times. With this information, we can then get these values from the Nautical Almanac, which tells us where each star was directly overhead for the times stated. These are the original sextant measurements, and after taking into account any index error, refraction or height of eye corrections, we can then get the true elevation angles to the stars along with their complementary angles. And as we discovered earlier, it's these angles that dictate the size of the circles of equal altitude, which when plotted reveal the position of the observer. Now, I've wrote this GeoGebra script in such a way that allows presets, and when selected, variables get updated based on what is written here, so let's go through them. This is the radius value in nautical miles. I'd set this to 6371 if I wanted to use kilometers. This is the date Proto Thad made his observations. This is where I'd input any index error. And this is the dip correction based on an observation height of 2 meters, and you can get this from the Nautical Almanac. Next are the specific star observations, so let's take a closer look at this one. This is the name of the star, and this is the time of the sighting. This is the measured sextant angle, and this is the Greenwich hour angle of Aries in 2 parts for the time above. This is the first part for hour 0, while this is the second part for 34 minutes and 49 seconds. This is the sidereal hour angle for Altair, and when added to the GHA of Aries, you get the GHA for the star, which in turn will give you the longitude of its GP on Earth. The latitude of its GP comes straight from the declination, while this last value is a tiny correction for refraction. The table updates when we click on the preset and the new circles are drawn. Zooming in shows an area where the observer is likely to be, and the coordinates are shown here. For scale, this side of the triangle is 6 nautical miles in length. Putting those coordinates into Google Maps, we get this position. Proto Thad revealed he was near Wind Point Lighthouse, which means this fix was only about 2.5 miles off.
Are you stupid? Let's go back to my drawing. This is a hypotenuse, correct? Yeah. This is what gives the co-altitude angle, correct? Yeah. You measure this angle, hypotenuse, over a horizontal to give your co-altitude angle, aka hypotenuse, used. The distance of this hypotenuse to the horizontal is what gives your curve.
So this about wraps things up. Proto Thad managed to get his position with nothing more than a sextant, a classroom globe, and big fat marker pens, and yet he was still accurate to within half a degree. Do you have anything to add, Flatzoid?
This is how idiotic these people are. This is how stupid you morons are. I'm saying it straight out. You are an idiot.
Wow.